In this problem, we wanted to determine if the mean value theorem applies. So again, hopefully you've checked this out in the notes where we describe what the mean value theorem is and kind of what it means. So hopefully you've checked that out in the notes. The mean value theorem has two conditions because it's actually a more generalized version of Rolle's theorem. Rolle's theorem guaranteed that you had a horizontal tangent line or a place where the derivative was zero. And it was able to do that because Rolle's theorem required your starting and ending points to be the same. That combined with continuous and differentiable guarantees at least one place where the tangent line has to be horizontal. The mean value theorem takes away that initial requirement. It says they don't have to be the same, but there still is going to be a place where the tangent line slope is the same as the secant line slope line between the 2 points. Or in other words, there's a place where the instant rate of change is the same as the average rate of change. I always think of it this way. The mean value theorem is just Rolle's theorem on its side. So if you kind of take this picture and rotate it so that that line was flat, then you'd see Rolle's theorem in the picture. That's how I always kind of visually think of the mean value theorem. So just like with the problems with Rolle's theorem, we're checking conditions. For mean value theorem, there's only two conditions to check. So let's take a look at what our function is here. Our function is 1 over x squared on the interval 1 to 4. On the interval here 1 to 4. And so we want to know, is this function continuous? Is it differentiable? Is it continuous? Is it differentiable? Well, is it continuous? Well, one of the things that might pop in your mind, well, wait a minute, 1 over x squared, if the bottom's 0, that's not defined. And that is 100% correct. However, being undefined at x equals 0 does not affect this problem, because 0 is not in the interval 1, 4. So the only place where this would be undefined would be at 1, 4. The only place where it would not be continuous is the only place where it would be undefined is at 0. So the only place where it's not continuous is at 0, but 0 is not in the interval 1, 4. And so therefore, yes, for our interval, this thing is continuous. So is it differentiable? Well, let's compute the derivative of 1 over x squared. Remember, you might want to rewrite that as x to the negative second. When you do that derivative and clean it up, you'll get negative 2 over x cubed. And for the same reasons above, that's undefined at x equals 0, so it's not differentiable at x equals 0, but 0 is not in our interval, so that's okay. So yes, the mean value theorem is going to apply. The mean value theorem does apply. So MVT does apply. And that's step 1. We've checked and verified. Yep, mean value theorem does apply. Now we want to find the values it guarantees. The mean value theorem says there has to be some point in the interval 1, 4 where the slope of the tangent line, in other words f prime of c, has to be equal to the slope of the secant line, the line between 1 over x squared, and 4, 1 over 4 squared, which would be 1/16. Right, so we have to say that there has to be a place where the derivative here is equal to the slope of that secant line, which in our case would be f of 4 minus f of 1 all over 4 minus 1. And here we're computing f of 4 and f of 1 using our function here. So f of 4 is 1/16. F of 1 is 1, and 4 minus 1 is 3. So we have 1/16 minus 1, which would be a negative 15/16 over 3, but dividing by 3 is the same as multiplying here by 1/3. Negative 15 over 16 times 1/3. 3 and the 15 cancel, and we get negative 5 over 16. So the slope of the secant line, the line between the points at x equals 1 and x equals 4 on the graph, is negative 5/16. The mean value theorem applies, so we're guaranteed there has to be some place in the interval 1, 4 where negative 15/16 is the slope of the tangent line. And so now we just solve. When is their derivative here equal to negative 15/16? So when is negative 2 over x cubed equal to negative 5/16? Well, we have a little equation to solve here. It's not overly complicated. We can cross multiply. 16 and 2 will be negative 32. Bring the x cubed over, we get negative 5x cubed. And then we need to solve for x cubed. So we divide both sides by negative 5. We get 32 over 5 equals x cubed. Take the cube root of both sides. We get the cube root of 32/5, which is about 1.86. So at a point 1.86, here, the slope of the tangent line is going to be the same as the slope of the secant line. Now I want to show this to you in a picture. I'm going to show you a graphical picture of this, so you can kind of get at least a feeling again, not just what the mean value theorem says, but really what it actually means. So here we are with a graph. This is the graph of 1 over x squared. You can actually see if I continue out, there's the two sides of it, but I've zoomed in here. So that we can see here's the line passing between the point 1,1 and the point 4 1/16. So I've drawn in that line here. That's the actual equation of the line if you are interested in that. And so what I've located on my graph here is my point there when x is 1.857 or 32/5 to the 1/3. Plug that into my original function. That comes out to be my y value there. Decimal of about 0.29. And then what I've done here is I've drawn in or put in my tangent line. Ugly looking equation, but what I just want you to see here is that tangent line is moving in the same direction, exact same slope as my secant line. And that's what the mean value theorem guarantees, is that we're going to have some point in the interval where the slope of the tangent line is the same as the slope of that secant line passing between the two endpoints. Or in other words, that secant line is your average rate of change. So there has to be some point in the interval where your actual instant rate of change is exactly the same as the average rate of change. And that's what the mean value theorem guarantees for us. And it turns out this mean value theorem is going to be useful to us in several scenarios in some upcoming chapters.